So now we're taking a look at section 7.1, linear systems in 3 variables. So as you recall, a system of equations, you must have the same number of equations as you do variables in order to solve the system. So with a system of 3 variables, linear system, we're going to have 3 variables and 3 equations. So a linear system in 3 variables is like finding where 3 sheets of paper meet. Okay, you've got 3 planes. There are 3 types of solutions. The first thing we can have is a single point. So notice down here, if all of those sheets of paper kind of cross in a way where they meet in one point, then we have one single solution. And notice it's given not as an ordered pair, but like an ordered triplet in alphabetical order, the X, the Y, and then the Z. It's also possible to have infinite points, but unlike 2 linear equations, when we've got planes, those infinite points come along in a line like this, okay? So we're going to write one of the variables as just the variable, but the other 2 variables in terms of that one variable. I know that seems like a lot, but we'll do an example so you can see it here in a minute. Third possibility is no solution. The example on the very right, you have 3 planes all parallel to each other, so none of them cross anywhere. But it's also possible for maybe 2 of them to cross at a time, but there's not one place where all 3 of them meet. In other words, it has to be a solution for all 3, not just 2. And remember, points represent solutions to the equations. Equations are represented by those points. So let's do an example of a single point solution. This is what we call a consistent system. So in equation 1, we have 3x minus 2y plus z equals 2. Let's call that equation A. Then 5x plus y minus 2z equals 1. Call that equation B. And 4x minus 3y plus 3z equals 7. We'll call that equation C. Now we're still going to use substitution or elimination methods like we've learned before. It's just we can only work with 2 equations at a time. So here's our goal. We're going to reduce it from 3 variables, 3 equations, down to 2 variables, 2 equations, down to 1 variable and 1 equation. Okay? So let's first get it down to 2 equations with 2 variables. So let's pick any 2 equations and get rid of one of our variables. A nice one might be, to get rid of the y, we can choose A and B. So notice equation A has a negative 2y. So we're going to write it as is, 3x minus 2y plus z equals 2. But if I want to eliminate the y there in B, I need to multiply equation B by a positive 2. So that would give us a 10x plus a 2y minus a 4z equals 2. Now we can combine these 2 equations and come up with a new equation. We'll call it equation D. That gives us a 13x, the y's are gone, minus a 3z equals 4. So now I have one equation with 2 variables. I need to come up with another equation with the same 2 variables, which means I need to choose a different pair, either A and C or B and C, and then come up with another equation where I've eliminated the y. So since the B already has a single y with it, why don't we use the B again? But this time, since we're trying to get rid of the C, we're going to multiply equation B by 3. So that will give us a 15x plus a 3y minus a 6z equals 3. And we'll leave C as it is, 4x minus 3y plus a 3z equals 7. So when we add these 2 equations together, we'll call that result equation E. We get 19x, our y's add up to 0, minus 3z equals 10. So now we've taken our 3 equations with 3 unknowns and we've whittled it down to 2 equations, 2 unknowns. So I'm going to take this E and I'm going to write it here underneath my D just so I can compare apples with apples. 13x, I have a negative 3z equals 10. And now we have to eliminate again to get it down to 1 variable, 1 equation. Well, it looks like the z's would be a good choice. So I need to take one of those equations and multiply them by a negative. So I'm going to multiply, let's say, equation E by a -1. So that will give me a negative 19, a positive 3z, and a negative 10. So when I combine those equations, we now have a negative 6x. Our z's add up to 0, equaling a negative 6. So when we divide both sides by -6, we get x equals a positive 1. So notice how we whittled it down. In blue, we still had 3 equations, 3 unknowns. Our resulting equations in green, we had 2 equations with the same 2 unknowns. So notice both blues, I got rid of the y's. If we'd gotten rid of the z's the first time, we'd had to get rid of the z's the second time. Be consistent. Matter of fact, write yourself a note. Must eliminate same variable. So now that we have x equals 1, we have one of our solutions. We are going to plug this into equation either D or E and solve. In other words, we're going to create another equation with only 1 unknown. So we can choose equation D. Equation D is 13x minus 3z equals 4. We're going to plug in 1 for x. So when we solve for z, we get z equals a positive 3. And now we have to find our y. So we're going to backtrack again and plug everybody into one of our original equations. So if we choose equation A of 3x minus 2y plus z equals 2, we're going to plug in the 1 for the x. We still have a negative 2y. We're going to plug in a positive 3 for our z and solve. So we end up with the solution of 1 point of 1, 2, 3. Again, x, y, z, we always put it in alphabetical order. Now we have an example where we're going to have infinite solutions. These are called dependent equations. The answer to one is dependent on the answer to the other. One of the things you may notice is that the x, y's, and z's are not lined up. I would definitely put them all in order and in line with each other so we can see them a little bit better. So our equation A at the top, we would write 3x plus 2y plus 5z equals 6. It doesn't change. Equation B, however, we have a 3y. Let's subtract that z from both sides. So we get a negative z or minus z equals 4. Notice how we've lined up the variables. And for equation C, the left-hand side only has a 3x. So let's line up our 3 x's. We're going to add that 17y to both sides. There is no z, so I'm going to kind of skip the z spot and then write equals 26. So notice how all the x's are lined up, the y's are lined up, z's, and so forth. Other than the fact that I told you this one's going to have infinite solutions, you can't tell by just looking at it right away necessarily. So we still want to approach it the same way we would approach any other equation. See if we can get it down to 2 equations, 2 unknowns. So we might choose, let's say, equation A and C, since our 3's are already alike. So equation A is originally, again, the 3x plus 2y plus 5z equals 6. We're going to multiply equation C by a -1. That gives us a negative 3x minus 17y equals a negative 26. So when we combine these 2 equations, we get a negative 15y plus 5z equals a negative 20. We'll call this equation D. And remember, we have to get rid of the same 2 variables, but one thing that we might notice is up here, we already have an equation that has a y and a z in it only. So we can just use equation B and try to get rid of one of the variables. Let's say that we try to get rid of the z, because the z is a -1. That means we need to multiply everybody by 5 in equation B up here. Well, 3y times 5 gives me a 15y. Negative z times 5 gives me a negative 5z. And 4 times 5 gives me positive 20. Well, notice what happens when I add these two equations together. We get 0 equals 0. Well, this is a true statement. So it means that there are solutions that exist, but there's multiple solutions. This is our hint that we have infinite solutions. Now, it doesn't have to be 0 equals 0. It could be 7 equals 7, negative 12 equals negative 12, even x equals x. Probably not, since we got the constants on one side, but you get the idea. It's going to be a true statement of some kind. So if that is true, what we're going to do is we're going to choose one variable. In this particular case, I would probably choose y, and I'll show you why. And then we're going to represent z as some equation with y. And we're going to represent x as some equation of y. Okay, so that would be our goal. Now, let me show you why I would choose y. Notice in equation B and equation C, both of these equations have y in it. But B, I could get the z by itself and have an equation with just a y. And in C, I can get an x by itself with an equation with y. So that would give us two really nice functions. So if I chose equation B, the 3y minus z equals 4. Let's subtract 3y from both sides. Multiply by -1, I would get z equals a 3y plus 4. So I can plug that in for my z to be 3y plus 4. And then I can do the same thing in equation C and get the x by itself with just a y. 3x plus 17y equals 26. 3x equals a negative 17y plus 26, and then divide everybody by 3. X equals a negative 17 thirds y plus 26 thirds. So that would be our x value, negative 17 thirds y plus 26 3. So notice here, one variable I chose is just by itself. The other two variables are represented in terms of just that one variable. So these can take a little bit of time to absorb what we're looking at. Now, unfortunately, sometimes when you're doing homework, they only see one possible answer. They do it in terms of always z or always x. So let's suppose with this particular equation, if we want in terms of x, it just means there's going to be a little bit more involved, okay? So we're still going to have our three pieces, our x, y, and our z. Oops, I was going to say in terms of z, not x. Z is just going to be z. So I need to get y in terms of z. Well, I know equation B up there. I can do that right away. 3y minus z equals 4. Add z to both sides. We get 3y equals z plus 4. And divide everybody by 3. We get y equals z plus 4 divided by 3. So that goes in the y position. Z plus 4 divided by 3. So no matter what value z is, it's some random variable, I can plug it into the y position and find my y coordinate. X may be a little bit more challenging, but notice in equation C here, where we have 3x plus 17y equals 26, I can get my x in terms of y, but not in terms of z. So what we would do is take this guy and plug it in for this y. So that would give us 3x plus 17 times z plus 4 all over 3 equals 26. Let's go ahead and multiply every term by 3 to get rid of that denominator. And we would get 9x plus 17 times z plus 4 equals 78. Let's distribute. And now let's solve for our x. So this would be the equation. X equals negative 17z plus 10 over 9, assuming I did all my multiplication and stuff right. And that represents my x coordinate up here, negative 17z plus 10 all over 9. So I'm representing my x, I'm representing my y, and my z is understood to be. Our last example is an example where there's no solution. It's an inconsistent system. So our first equation here, negative x plus 6y minus 3z equals a negative 8. We'll call that equation A. X minus 2y plus 2z equals 3 is equation B. And 3x plus 2y plus 4z equals a negative 6 is our equation C. So once again, we want to eliminate one of the variables twice. So let's pick two of the equations. We can get rid of the x's or the y's. Why don't we get rid of the x's this time just to be different? Because they're already opposites in equation A and equation B. Since we don't have to multiply anybody, we can go ahead and add those together. The x's add up to 0. Our new equation D would give us a 4y minus z equals a negative 5. We're going to pick two more equations. Let's choose A and C this time. Since A is negative 1 and C is 3, I'm going to multiply equation A by 3. That will give us a negative 3x plus 18y minus 9z equals a negative 24. And our C is already a positive 3x plus 2y plus 4z equals a negative 6. If we add those together to get our new equation E, we got rid of the same variable of x. That leaves us with a 20y minus a 5z equals a negative 30. So we're going to write the E under our D here. Now we want to be able to eliminate these. So I would probably choose, well, let's get rid of the y's. So I can multiply the top guy by a negative 5. So a negative 5 times D would give me a negative 20y plus 5z equals a positive 25. Equation E we can leave as is. But notice what happens when I add these together. The y's add up to 0, the z's add up to 0, and we get 0 equals negative 5. This is a false statement. As soon as you get a false statement, 0 equals negative 5, negative 10 equals 15, anything that's not true, that tells us there is no solution. We like these because they're quick. As soon as you get that false, you're done. If you get a true statement, there's more work to do. All right, that is it for solving systems of linear equations in 3 variables. If you have any questions, don't hesitate to ask. Come see me, go to the Math Success Center, go see your teacher. We're all here to help. That's what we're here for. Bye.